Okay. Hello, everyone. It's welcome to the Brain Space Initiative. It's a pleasure to have you. We have the pleasure of having Conrad Cording today, who's going to talk to us about causality. So just to kind of briefly introduce Conrad, he did his diploma degree and PhD at ETH Zurich, and then worked as a postdoc at Collegium Helveticum in Zurich and at University College London. He then did a Heisenberg Fellow position at MIT, joined the faculty at Northwestern and the Rehabilitation Institute of Chicago, where he was a professor of physical medicine and rehabilitation, physiology, and applied mathematics. Is that all, Conrad? No. And then since 2017, he's been at the University of Pennsylvania in the departments of neuroscience and the Department of Bioengineering. So he is also the sort of an instigator of this sort of very innovative training program called the NeoMatch Academy, which he'll probably mention in his talk, doing sort of lots of new ways of teaching with teams. Today he's going to be talking about causal statements and functional connectivity. I think he's hoping to correct the neuroimaging field. And so we will see what he has to share. And what I would say is that I think I said something on Twitter that caused Conrad to give this talk. So is that a causal statement, Conrad? So
counterfactual. Maybe I would have gotten invited nonetheless.
Yeah, so it was perturbation though. So anyway, so it's great to have you. We're looking forward to hearing what you have to say and to discussing it. So without further ado, I will pass it over to you.
Wonderful. First, thanks so much for having me there. And I will talk about very generally about causality and what we can and what we cannot know. So let me start right there with the definition of causality. And this is the definition that I use. And I will argue that most people that talk about causality are implicitly using the same definition. So my definition is, let A and B be events. And when I say events, it could be it could be the activity of a neuron or of a group of neurons, or it could be A could be if you smoke, and B could be the activity of another neuron, or it could be if you die. It can literally be any kind of an event. And my definition of causality, which is the standard counterfactual definition of causality, is if we had changed to A to A star, then the probability of B would have been different. And it's clear if we can do randomized experiments, we change A to A star a couple of times, maybe even sometimes disagrees with me on Twitter, other times he doesn't disagree with me on Twitter, and then we observe B, which in this case is, say, does Conrad get invited somewhere to give a talk about causality? And then if we can do these experiments, we can establish that there's a causal effect of one onto the other. That's my definition. I argue that there's a lot of people talking about philosophy of causality, but what I argue is that pretty much anyone who uses it really means it in this way. And I'll be happy to later on at the end of my talk discuss what we mean with that. So now causality is of course legitimately important in lots of scenarios. So you can say, in life, causality is what life is about. We can choose one thing, or we can choose to do another thing. Arguably, what we try to achieve in our life is choose the things that sort of make the world better, or at least make our life better. And where we stand on that continuum is, in a way, very characteristic of a person. Now, you can say equally causality matters in neuroscience. For example, in medicine, we want to predict which perturbations, if we would do them, will produce an improvement in the condition of the patient. And so in that sense, in medicine, virtually all questions that ultimately matter in the end are the causal questions, namely what makes a patient be better. And now you can say even within neuroscience, say, more computational parts, there's a deep drive towards causality, where a lot of people define understanding as getting at the causal chain, getting in a way at how neurons, groups of neurons, basically process what goes into our eyes, do something to it, and ultimately give rise to behavior. And for a lot of people, in fact, the definition of mechanism is that we have a causal chain where we understand the components of that causal chain. That's what a lot of people mean with mechanism, and mechanism is what a lot of neuroscientists mean with understanding. Now, let me start with how I started in functional connectivity. And I want you to see where I was coming from. So it was in the early 2000s, and I had just started my lab at Northwestern University, and we were collaborating with people doing experiments in motor cortex. Lee Miller's lab, wonderful labs. And back then, people started looking at correlations between neurons in a way as a measure of what they do with one another. And when we started thinking about it, we started focusing very much on the role of explaining away. So let's say we have a causal chain like we have in the top left here. If we have this causal chain, A excites B, B excites C, what will we see? Well, we'll see that A and B have some correlation structure. And of course, B and C have some correlation structure because they're directly connected. But we will also have some correlation structure directly between A and C. And if you want, these two here correspond to causal interaction. This one corresponds at least to an indirect causal interaction. Similarly, in this case, if A drives B and C, these two correspond to causal interactions. This one is just common input. So the idea that we had in the early 2000s is, well, we shouldn't be using correlations because they have this problem that they will basically, we will see correlations even if it's either a chain or if it's common input, and there's no way of separating that. Now the idea was, if we instead do model fitting instead of correlations, we could get rid of that. And that's what we sketched here on the right-hand side. If we basically do a joint fit, then that effect will go away and it will not infer that there's a link from A to C. So this is, of course, all simulation data, and I should say this is from a review of a wonderful student, Ian Stevenson, who's now professor at Connecticut, and all these studies done by him. And so how can we do that? So as some of you may know, I used to be very Bayesian, and oh, hold on, talking about Bayesian, together with Wei-Ji Ma and Dan Goldreich, we wrote a book about how to learn that teaches Bayesian techniques. It's called Bayesian Modeling of Perception and Action, and we just dropped it on Twitter for pre-review. And I want to invite everyone who's interested in Bayesian methods to read that book. So it's meant to be a very, very gentle introduction to Bayesian thinking, in particular about Bayesian thinking when applied to how people learn. So we talk about, say, how humans might integrate prior knowledge with new information, how they would do Q combination between two things. And we're currently looking for people to give us feedback on how we could make that book better. But let me not be distracted there. So the idea is we here built a Bayesian generative model where we had hyperparameters that basically select how probable it is that neurons are connected, things like that. Then based on these hyperparameters, we believe that we have a connectivity matrix. And what I sketch here is what's called the generative model. And then you can say, based on the actual connections, we will get spatial temporal kernels of how neurons interact with one another. Based on those, we will get firing rates, and based on those, we will then ultimately get spikes. So firing rates, if I say that, I really mean the conditional intensity function. So this was a popular way of analyzing data back then. And indeed, if we set up the model like this, it will have the possibility of explaining away. And if we look at the modern literature using functional connectivity or effective connectivity applied to brain data, it very much goes for this notion of explaining away that basically we can get rid of certain relations, certain correlations, or explain certain correlations based on causal interactions between different parts. And I should show here, it works wonderfully in simulation. So what we did here is we simulated 4 mutually connected neurons on the x-axis here. So you see each of the 4 neurons, to each of the 4 neurons here, 4 by 4. In black, we have ground truth values here. In red, we have what our Bayesian maximum posteriori system does, and in gray, we have what we have if we don't use bias. And in general, we can see that we can identify these systems well. Now, let me just zoom out what I did here. I simulated neurons according to this model. And then I showed that the statistical procedure, and when I say I, of course, I don't do anything. Ian Stevenson did that. And what he showed is that we can recover what we put into the simulation using our data analysis procedure here, which is something that we should always do when we do any data analysis, because a mistake in our analysis routines will mean that the estimates that we get out will usually systematically differ from the true values that we put into our simulation. Okay, and then we also applied this algorithm to real neurons, and we were kind of happy because we get results. Now, like we found some neurons to be significantly related to one another. We also found that basically there was something in the data that went just beyond the distance of them in space. So we did a couple of controls. Now, what does it mean what we did so far? And the way I viewed this work back then is it's a way of doing things better than correlation. And much of what this talk is about today is how over time I think I get more critical about thinking about this. So let's first see what was in the paper. Now, in the paper, we said the main difficulty is that these and virtually all other approaches to functional connectivity face is that correlations between new neurons can be caused by both interactions between observed neurons as well as unobserved common inputs, such as those arising from external covariates. But it's not just those arising from external covariates. It's also those arising from neurons that we don't record. Now, going back into the experimental setup, we are analyzing Utah grids here. So this is a device that's 4 millimeter by 4 millimeter that records from order 100 neurons. Now, we have order million neurons in a cubic millimeter, if I remember that number well. So that means that we record 100 neurons out of many, many millions of neurons. And so let's think a little carefully about it. So we have a tiny, basically 0% of all the neurons that we have there. Now we know that each neuron has order 7,000 inputs. So the expected actual causal inference of one neuron on another neuron should be very, very small, in particular if they're on different electrodes, which our neurons typically are. And yet, we get like these nice interaction kernels. And it seemed credible, those interaction kernels, in a number of ways. And now, what I'm telling you right now is a thought that I didn't have back then. And over the last decade and a half or so, I thought a lot more about this space. And that leads me to give the talk that I'm giving today. But I want you all to know that basically I started my scientific career as a professor doing functional connectivity modeling. Okay, and now let's fast forward a little bit. This is a wonderful review paper by Reed et al., where the title was Advancing Functional Connectivity Research from Association to Causation. So what's the idea? We have causal interactions at the neural level. Now we make observations, and those observations will of course be somewhat more more noisy and we'll observe from multiple areas. But the idea is then we want to get from there. And of course, there's confounding. And we'll talk a lot more about confounding. And the idea is, can we from there then get back to something that approximates what we have at the neural level, something that characterizes the causal interactions that we have in that area? So what's the idea? The idea of that paper, and just to already give away the punchline, I don't believe what the paper says we should be doing is actually possible. But here's the idea. We have one method. It has confounding. There's problems with that method. Every method has problems. It gives us some parts of the hypothesis space that are compatible with that data, the blue parts. And then method B equally has some confounding, some problems, gives us parts of that space. And by looking for the intersections between these spaces, we can lower the space of possible hypotheses. And the bulk of my talk today is that I will argue that no, this is actually not possible. So let's go through that. The first thing I want to point out is that we have very unfortunately gotten addicted as a field to the notion of causality. For grants, for papers, for talks, everyone wants to hear and think about causality, which is very natural. So human life, in a way, centers around a notion of causality. It's really useful for us to causally understand how things work, because that's what we need in our lives. So we have this very natural, as humans, drive to wanting to understand causally how things work. Unfortunately, if we don't make causal claims in our papers, the world will just reject our papers and grants and will be unhappy about our talks. And I will argue that that's a huge mistake. And I will argue that it has negative effects. And let's first look at language. The language we use in the field absolutely reflects that we want to make causal statements. And why do we use the word in Granger causality? Well, it contains the word causality. Why do we call it functional connectivity? Functional means that something has an influence. Connection means that there's a wire. Why don't we say correlation matrix? Well, we don't say correlation matrix because we want to make causal claims. We take the word flow. Flow means that something starts from somewhere and is moved to something else, suggesting a causal direct chain. Stuff being effective means it has an effect. It's a causal claim. All the words that we use are chosen, and in reality, they evolved. The words that we have in our field evolve. People write papers. Some people will use the word correlation matrix. Others will use functional connectivity. The people who use functional connectivity, their papers get cited more. Therefore, the word functional connectivity ultimately wins out in the marketplace of ideas. And I will argue that there's a problem with this. So let's also briefly do some introspection. We did some literature analysis where we asked which proportion of papers within science contain the word neuroscience. And we reached peak neuro sometimes in 2010. I should update this graph sometimes. And then we looked at the proportion of papers in neuroscience that talk about connectivity. And we can see that this is growing very, very rapidly. And with that, of course, comes the need for us to ask, well, what is connectivity exactly doing for us? What are we hoping to get out of this? So let's first get some intuitions about causality and what makes it easy or hard to get there. So we're gonna, and I should say, Vince mentioned NeoMatch Academy. NeoMatch Academy is this wonderful, extremely curated set of materials to learn the basics of neural data analysis. It was driven by a large community of hundreds of volunteers, and it has a day focused on causality. In fact, the very last day. And what I will show you in the next few slides is an example of that. Anyone who has ideas or maybe disagrees with me about this interpretation, all the code it's very easy. It's all on Google Colab. You can literally be running all the codes that I'll be talking about in less time than it takes me to get through this slide. So let's simulate the easiest causal system because it will help us get an intuition. We set up a dynamical system where we have xt plus 1. The idea is that x should now be a model in a way of neurons that interact with one another. So we have xt plus 1 is some sigmoid sigma. We don't necessarily need that sigmoid, but we'll use it because it keeps everything into a nice range. We can use the linear version of that, no problem. Is sigma, which is a sigmoid, off. And then we have axt. Now, A is arguably the causal matrix. Now, A contains which neuron in our simulation interacts with which other neuron. axt plus epsilon t. Now, xt is an n-dimensional vector representing our simulated n-neuron system at time step t. Sigma is the nonlinearity. A is an n by n causal matrix, how strongly each neuron affects every other neuron. Epsilon t is Gaussian random noise, isotropic, and we initialize x0 to 0. Now, like here we have a full model. Now, what do we expect there? If one neuron strongly influences positively another neuron, we should often find that one neuron is active, and then at the next time step, the other neuron is active. So one simple way of thinking about correlation is that we're going to use the delay one correlation. It's not like where we can say the correlation matrix C is xt times xt plus 1 transpose, so that we get that full matrix. And now intuitively, therefore, we expect that C somehow approximates A. And let's see if that's true. And yes, it is true. Now, what you see up there is the connectivity matrix A. And as you know, I can always take a matrix and represent it as a graph and the other way around. And what we have down there is the correlation matrix. And look, those two are extremely, extremely similar. And I should say, how did we choose the matrix A? We choose the matrix A to be somewhat sparse because we want it to be a model of how brain circuits work. And we also made it that the system is stable. So we made it that the largest singular value of the matrix is 0.99. Okay, and here, so correlation is roughly causation, and therefore the two of them are the same, and therefore Conrad should stop his talk right now. No correlation is causation, all problems gone. And unfortunately, that's not the case. Correlation is often causation if we have a very small system. So let's not take the same system, the same equation, no changes to it, and use it with 100 neurons instead. And this is what we can see there. On the left-hand side, you see the true connectivity matrix. On the right-hand side, the estimated connectivity matrix. Again, this is just the delay one correlation matrix. And wow, the correlation, those two are now almost entirely different. Why are they different? Well, if we have this small system that we can think of easily, 5 neurons, our intuitions are really good about what's going on there. If we have these big systems, they have their own modes, they produce their own activity. The noise that we add to every single neuron is basically no longer all that important because it's the population that makes strong activities. And therefore, that similarity between correlation and causation is effectively going away. Now we can quantify this here. On the x-axis, we have the number of neurons that we have in our simulation. On the y-axis, we have the correlation between the correlation matrix R and the causal matrix A, and we can see how that goes down. So at 5, it's extremely high, approaching 1. At 100, it's at 0.2, and it's starting to get very, very small. Now, this is kind of interesting, no? And I think it gives us an intuition on why we as scientists are so bad at thinking about causality in small systems, in the kind of systems that we can simulate in our head. Correlation and causation are the same thing, or at least very similar, unless we construct the small systems purposefully so that they're not. Whereas here we have, as we go towards big systems, they become very, very different from one another. Now, of course, we will dig into it and get much deeper intuitions. But this is the first thing that I want you to know. Like, as we make systems big, correlation and causation gets to be very, very different. The human brain, n of 10 to the 11, is a very, very big system. however we want to think about it. It's extremely big, and therefore correlation and causation should have absolutely nothing to do with one another. Now let me talk about the next issue, which is the so-called omitted variable bias equation. So we can mathematically solve that in the case of linear systems. If we have nonlinear systems, all the problems I'm talking about are just as bad. In fact, in many cases, they're worse. So let's talk about the following problem. We record some data, xi, vector, over time. And there exists causal connections of these x onto one y. No, maybe also the variables that we record from. You know, like if we have an autoregressive model, we relate variables at one point of time to the variables at the next point of time. But we now also allow that there's some variables that we don't record, the zi. They also have causal effects. In fact, the causal effects delta that they have should be of the same order of magnitude as the causal effects beta that we have between the variables we actually observe. Now, of course, we have noise here. Now we will be doing linear regression in this case. If we do nonlinear regression, again, the problems exist just as well. So what we have here, as in always in linear regression, we have this term, which is the inverse of the autocorrelation matrix of basically X with itself. And then we have here X prime, and then we have one term, X beta. These are the real causal effects. And we have plus Z delta, those are not the causal effects from variables we don't observe, plus U, which is just noise. Now, what do we get there? The expected value of this estimator is the causal effects. This is great. Plus, and then we have this term here, the inverse times X prime Z times delta. Now, what's X prime Z? Now, that's a correlation of the variables with with the unobserved variables. We know that neuron-neuron correlations are generally of the order of 1. Like neurons might be correlated plus 0.1, minus 0.1, so they are big. So now let's think about this term. It has this one term here, which is what we're interested in beta. These are the causal connections between the variables we record from. Plus, and then here we have a term that just looks like that first term, only that it's about all the others. Now, let's look about the magnitude here. Beta is order 100, order 1,000, depending on how many dimensions we record from. This term here contains the 10 to the 11 minus 100 or minus 1,000 variable interactions that we don't record from. Now, when I tell people, like, look, there's the omitted variable bias equation, they tell me, well, yeah, like, how many more subjects do we need? No, this is the bias that remains in the limit of an infinite amount of data. So this is not going away at all by scanning more people or recording from more animals or something like that. No, it doesn't go away at all. This is in the limit of infinite data. So in that limit, we should expect, if we record from a small number of dimensions relative to the overall system, all these things being equal, that this term will be arbitrarily larger than this term. So therefore, logically, we should not expect that we can at all get at causality from those kinds of methods if we don't observe the majority of variables. And I should say, the problem exists for all approaches. Now, in Granger causality, same thing. DCM, same thing. Information flow, same thing. And make it nonlinear, you still have all these variables in there, and there's no way of distinguishing these two. They're just simply correlated, and so you can never know. So now let me make things worse. Now you can say what I said before is feels like mean because I talk about techniques that say are popular maybe in the imaging range. Although I should say my background in functional connectivity is in spike analysis, and it's equally affected by these considerations. So let's now imagine we could record from all neurons. Now let's just think it through. We can record from all neurons, which means not only do we have the neuron, but we have all the presynaptic neurons. Could we then do causal inference? Well, let's see. What we want to do is we want to estimate the weight vector of the neuron. We call it beta because the causal inference literature generally does. So, and we want to do linear regression, and we have recorded absolutely every neuron, which isn't going to happen anytime soon, but like we have Stephenson's law, which will eventually rescue us there. So what do we have here? That estimator is going to be going to have two terms in the variance that it will have. The one term here is the square root p over n. This is a term where n is the number of samples and p is the number of dimensions that we have. What that just means is that the more dimensions you give me, linearly, the more data I need. No, so basically, if I want to fit a model between of neurons which have 10,000 presynaptic neurons, or 7,000, I think is the cortical number, I will simply need 7,000 times as much to get this term to be equally good. But it gets worse. No, so that first term that we have here depends on the correlational structure. Now, if the stimuli were white, then this would be 1. But of course, that would mean that I would have to stop all neural activities because neurons are correlated to one another. Now, how long would it take me if I took just 2 neurons and I make one of them spike arbitrarily how I want to figure out what the weights are? Well, you can say a typical paradigm there might take 5 minutes, might take 10 minutes. If we have 1 spike per second, it will take us 100 seconds to get 10%. Now, if you can say we have 7,000 presynaptic neurons, we need 7,000 times that number, which might take 6 days. But that's not nearly enough because this covariance structure looks very different. So what we can do is we don't know how that looks like for the presynaptic neurons of a given neuron. It might look better than if we generally estimate it with SVD, or it might look worse. But here's, for example, from Stringer et al. 2019 paper, you can see that we have some dimensions with a lot of variance and many dimensions with very little variance. Now, the important thing here is the so-called condition number, which is the ratio of the big singular values relative to the small singular values. And that might give us an extra factor 10 to the 3 for the first term there, which then means that we need to record for years to figure out even a 1,000-dimensional input vector for a given neuron. So even if we could have all the inputs, it's unclear if we could do that. So these are the 2 main areas that I wanted to give you intuitions about. So we are causally, as soon as we go higher dimensional, things are very, very difficult. From a power perspective, as we go high dimensional, things get really, really difficult. Keep in mind, this is the linear estimator that we have here. As soon as we allow interesting nonlinear things, things just get worse. But we have most power if we sit in this linear domain here. And in any case, it would take a really, really long time. So summarizing, if you want, it's difficult because of omitted variables. Even if we didn't have omitted variables, it would be difficult because of pure power considerations. Now, let me talk about a few other approaches to independence. So there's, for example, to causality, the causal discovery. Now, there exist, a lot of you might know the work of Gleimer and Spertus and Shinius and so forth, that say, let's estimate sets of potential networks that we could get, of causal networks, based on detecting independence. So let's think through that a little bit. The first one is over the timescales that our techniques, say imaging techniques, give us. I think we can all agree that no 2 brain areas can be independent because we know that within cortex, say, every brain area is connected with a small number of synapses with every other brain area. Now, what that means is that ultimately, in every synapse takes maybe 10 milliseconds for the signals to get through that, which means that we know for sure that there's a causal influence. We don't know what the size is, but we know that there's a causal influence of every area on every other area. So at some level, if we get a sparse graph, then every connection that's missing over the timescale of our signals will be a connection that we somehow dropped out of it. So that's the first thing. No, ground truth is fully connected. So that's a problem for the analysis. The second one is, what does it mean how can we detect that two variables are independent from one another? No, because we expect that things, suddenly when they have, say, some distance of one another, neurons will have a very, very weak effect of one another. Brain areas might have a very weak effect of one another. So our null model is a null model that has a lot of the probability mass very close to zero, which means that it will take an insane amount of data to convince us that this is actually independent versus that it's just a small correlation. The third one is these methods generally assume that there's no cancellations. It's called the faithfulness assumption. The problem of the faithfulness assumption is that whenever you have regulation circuits, then ultimately you have what's called cancellation, where you have an input that is guaranteed to effectively have no output. So in any case, I don't have time to go through the details of that, but I just want to point out that there exists problems lurking with all the techniques that I know that look for causal interactions. Now, let me go back now. What is it that I talked about? So in my view, none of the methods can provide meaningful evidence for or against causality. Why not? They can't possibly be powered. And there's all this unobserved dimensions, no? And so when I talk with people, they're like, yeah, but we record from all brain areas. Well, but within each brain area, there are lots of dimensions. In fact, if I record from spikes from some brain area, it's not that everything that it looks like a mean field model where all cells basically do the same thing. You know, like all cells do different things. And if I fit tuning curves for that, they have tuning in many, many different dimensions. So basically, yes, we record a tiny number of the dimensions. And now I can make this concrete. Look at this here. The fast PC, which would be the best you could hope to hit if you, say, measure the average activity in a brain area. Yes, it's bigger than the others, but it's not much bigger than number 10, and even not bigger than the number 10 to the 3 to the final number. So in any case, those are the prompts. So now, so the first thing is basically none of these techniques at all are indicative about actual causal relations, at least not by their statistical properties. No? They might randomly be correlated. They might be correlated due to some other modeling assumptions that we don't have on the table. So in that sense, they don't actually give you small colored boxes. They basically would make everything mostly blue. The second thing is that I think we're thinking wrongly about hypothesis spaces. Neuroscience is not of the nature that there's a small number of competing hypotheses, one of which is true. If one of which is true, then sure, sequential Bayesian model selection ultimately will get us. But instead, if we talk about, say, models where we talk about neurons and their interactions with one another, what's the size of the hypothesis space? If I allow 10 different weights between connected neurons, then we have 10 to the 10 to the 15 different models. Now, if we are in a small space where it's like maybe we have 100 hypotheses, sure, an experiment is great. It might not lower that from 100 hypotheses to 50. And we just need log of the number of hypotheses and we'll be there. If we live in one of these really big hypothesis spaces, sure, I might like lower the space by a factor of 10, which would be really good for a typical experiment. And then it brings us from the 10 to the 10 to the 15 dimensional space to the 10 to the 10 to the 15 minus 1 dimensional space, which for all practical means is 10 to the 10 to the 15. So that idea of making progress by sequential hypothesis spaces is predicated on an assumption of simplicity. That assumption of simplicity in the space of meaningful explanations of how the brain works might simply not be true. Now, the upshot of my talk is that I'm talking about infinitely confounding. If we have lots of unobserved confounders, we simply can't do causal discovery. Now, let's be clear where that's coming from. If I'm in the field of recording from spikes, as much of my own analysis about, we record from a small number of neurons. We effectively, unless we're in very specialized systems, we record from 0% of the overall population. Similarly, when we use, say, imaging, e.g. EMG, LFP, we record from lots of neurons, and they encode lots of different dimensions. But all what we do is we see basically the average of all of that, which means that there's lots of dimensions that we don't see, and therefore we can no longer say anything about causal inference in those spaces. We record 0% of the dimensions, 0% of the relevant information. And I want to argue that we all know this problem with causal inference, and it's reflected in the canonical paper structure of applied papers. So the abstracts usually say we want to understand something really complex. The introduction, here's that entire field, all these ideas, and they're beautiful. And then the results section is, so let's measure some correlations. But we use causal words when the statistical techniques allow us, and we usually have a paragraph somewhere that says, yeah, we know full well that correlation isn't causation. And then we look into the discussion section, and then we interpret our results as if it was causation. And I should say my own papers from the early 2000s have exactly that structure, where I said, yeah, and there's some papers from the 70s and the 80s that kind of say that, like, we can still get the right things. And why do we write these papers? Because we want to write causal papers. The fact that we can't is just like, well, we want to write those. And I want to say, why are we still doing that? Because we have had so much progress in methods that actually give us causal techniques. Now, we can stimulate brains in lots of ways and see what's going on there. It's a perturbative method. Perturbative methods have no trouble in establishing causality. They are low dimensional, and that makes it harder. But we can say we might want to see random perturbations and see what the effect is. We might want to change the locations. We might want to, like, cross-link lesion studies, which are causal. They have their problems. Now, like, don't get me wrong, they have all kinds of problems with stimulation studies. There's all kinds of things that we have there. And I want to say one more thing. I'm not even sure that we should strive towards explanations of brains in terms of causality. So if I give you a neural network trained on something, arguably causality is undefined to useless. No, we have millions of weights. Can we understand those weights? No. Do they have some modular structure? Yes. If we do PCA on it, does it look a little like brains? Yes, it does. But we don't know how to interpret it, or if that even needs to exist. So arguably, another way of thinking about what we want to have is get at objective functions, things that the brain optimizes. How does the brain optimize it? Architectures. There's a lot of wonderful research that we could do in anatomy if we try to bring computational approaches together with anatomy, and if we would start looking at learning. And a complex learning system doesn't have simple causal answers. So if say the brain learns itself using something like backpropagation of error or something, yes, we do expect that the interactions between brain areas are wild. They might, if we look at them in a low dimensional space, they will have some structure, but that structure doesn't really describe what's going on in the system. So with that, my take-home message: causality is central as a goal in much of neuroscience, but it's very hard to obtain in practice. And if we only do partial recordings, causality may usually be impossible to obtain. And even if we would record all neurons, then power might be a major problem. So even then it might be impossible to get there. And lastly, maybe causality should not even be what we want in that space. And thank you all for listening. Oh yeah, and of course, none of the things that you heard about was done by me. It was all done by my wonderful lab. Thank you. Oh, and I should say also, hold on, I totally forgot that. Much of what I talked about is from a joint paper with David Mailer, and who I believe is in the audience, or maybe in the audience. And he's done all the creative work here, and he's done a wonderful job. And thanks everyone for being here.
Thanks, Conrad. Great talk. Let's see here. So I'd encourage everyone to ask your questions. Conrad has thrown down the gauntlet. So let's let's get some discussion going. Got a few questions. Armin, am I able to share my screen? I can't, right?
Let me just give a second
Okay.
to make you.
I found a relevant.
Okay. Now you're the presenter.
All right. Okay. So let's see. Can you guys see that?
Yes.
I found that a relevant PhD comic topic, which it partially gets at something not Conrad's not getting at, which is really once the science is done, what happens after, right? In terms of causal statements, right? I think so. I think that's also an issue. I think Conrad, you're also talking about statements within this box too that can potentially further exacerbate the issues. So anyway,
absolutely, yeah.
Yeah. So.
No, and I mean that just shows you as scientists, we have a drive towards causality, even if we shouldn't talk about causality. And then everyone else is even more extreme in that direction. The journalists want it, and the readers, and our grandmother wants it, and that just puts us into a really, really tough spot here.
Yes. Yeah. I would sort of say that sort of early on, you know, because I started sort of right around the fMRI beginning days. And I remember all the debates and arguments about we can't measure neurons. We're so far away from neurons. This is like putting your hand on the hood of a car and feeling is the engine warm, and then saying something about the engine, right? And so I think the scientists, at least based on those discussions, you know, are well aware of the limitations, many of the limitations, although I would say that I would agree with you that language can sometimes be sloppy, and maybe it can go beyond that. Sometimes there's statements beyond sloppiness, but.
Yes, so let me push back a little bit.
Okay.
So I think that all of us old people are well aware of people like me who are old. I think we're quite aware of that. But I think for people who join the field, at first things are very difficult because we have all these words that won out over time over non-causal words. So the exact logic of the underlying science, it takes students a long time to get there and to know that they don't get causality. And it is interesting, you know, like if you look at, say, the way Carl Freston communicates in his talks, it's very opaque which of the two of them he means. He's very clear that he's not establishing causality in the brain, that it's just a matter of comparing models. But that is suddenly not the way it's perceived by students I'm talking with. And that's why I'm giving this talk.
That's a great point. See, I told you we agree. Okay. So let me just.
Yeah. Yeah, I mean, I can take questions, or do you want to read the questions?
I will. Yeah, I'll read them to make it easier for you. Roger Silva had asked a question about the correlation matrix that you presented. He said it's not symmetric because of time delay between xt and xt plus 1.
That's right. Yes.
Okay.
No, like it's so I have an asymmetric interaction model, which should mean that in small systems, if one neuron is active, it makes the other one active at the next point of time, but not the other way around.
Okay.
No, if we would have very low pass signals, it would look like the symmetrized version of what we have here.
Mm-hmm. Spencer, did you want to ask your questions? You can unmute yourself if you'd like. You said, I have a few questions. Spencer Kinsey.
Does he have permission? That's I think.
Armin, is he able to unmute Spencer?
I can do that. I can do that.
Okay.
Needs permission.
Yes. While we're waiting for him, Dabi Ranav has asked if we are so hopelessly far from causality, shouldn't TMS lesion cooling studies work much less frequently? or are these at a different level?
So TMS and cooling studies are real causal perturbations. If you randomize how you cool or you randomize how you TMS, then there is no threat to causality at all. The interpretation is hard, like because we have a complex model, like the TMS signal produces something locally, it's not entirely local, but we do know then that whatever happens related to it is on the causal chain of this local perturbation that we have to what ultimately happens. There's of course methodological problems, like the perturbation of zapping someone, they also hear it and so forth, and people need to be very careful. But when done properly, any of these studies establishes causality. Now you can say, why do if our approaches that we use for causality are so hopeless, why is it that sometimes if we're inspired by these studies, stuff actually works? And to that, my answer would be, A, it doesn't very frequently work. Otherwise, we'd have much more clinical applications of things. But B, if you want, it's the only, every stimulation study more or less is at some level inspired by a literature that confuses correlation with causation. And therefore, any progress at scanning, at stimulation, will kind of by definition, by society construction, look like it actually showed that there's something real about the way we've been thinking about correlation versus causation, because the bulk of experiments are at some level guided by these studies.
What is your opinion on in relation to causal statements in optogenetics? I think you would agree that that's also causal, but go ahead.
Optogenetics is causal, but let's be clear about that. And
causal statements.
And we have some criticism there. So there is no doubt logically that optogenetics establishes the causal link of light going in and the behavior that you measure, or whatever it is that you measure. There's no doubt about that. That's super clear. There are major doubts about the interpretation of that. And we have, for example, we have a paper where we talk about optogenetics is somewhat non-local. So it turns out that if you have your construct in all mouse cells, then you induce more spikes at a large distance from where your light goes in than close to it, and therefore it's a non-local technique. So it leads to interpretation problems, but it establishes the causal link between light going in and what's happening. Of course, if you have a local virus injection, it gets to be much more precise.
So can I unmute? I'm going to unmute Spencer.
Okay.
Yeah, can you hear me?
Yep.
Yes.
All right, thank you very much. I don't know if you can see me. It doesn't look like the camera function is working. But thank you for a great talk. I really appreciate it, Dr. Cording. I've studied some of your other papers, such as Could a Neuroscientist Understand a Microprocessor, which I found really, really interesting. I'm currently a second-year philosophy student in the MA program here at Georgia State. So I'm earning my MA in neurophilosophy and studying philosophy of neuroscience with Daniel Weiskopf. And so a lot of these issues came up in a philosophy of neuroscience seminar last fall. And a lot of them have been on my mind since then. And my thesis work is related to the prospect of localizing representations in the brain and just how difficult that is when you get down to the implementation relation and trying to identify which, symbols or icons are being operated over, or how to distinguish data and process. This seems almost hopeless sometimes. So I'm wondering, I think that your criticism of the kind of the language being used in a lot of scientific literature is completely valid and really, really interesting. But I'm wondering, I guess for one, how much closer do you think perturbative methods are actually going to bring us? Because you had mentioned the example of perturbing a brain area and then demonstrating a movement of the hand, or that it doesn't move the foot or something to that effect. But in systems in the brain where you've got this level of integration and these feedback loops, using perturbative methods to try to demonstrate causality between brain regions rather than behaviors seems to be drastically more complicated because of off-target effects.
Yeah, and it's not just the off-target effects. No, like at some level, there's from my perspective, there's a major problem with the underlying model that we have there, which is at some level, if all you can measure is the average signal from brain areas, it leads you down a role where you want to think about the brain in terms of models about you have kind of brain area activation, making another brain area active. It's interesting how basically there is this model that basically talks about brain area interactions in the imaging field, while there's models about neuron interaction in the neuron field and models about spine integration in the single neuron recalling field. And like they all look at their level. When it comes to brain region interference, so like in a way it's fine if you can locally stimulate. Like I know there's like en passant accents and all kinds of things like that, but if you can locally stimulate and you look at a little later, what do you have at the next space? Now, the big problem, of course, is time scales. And like if I wanted to know, do signals from my stimulation here like end up here? I would want to know, like it will take 10 milliseconds, something like of that order of magnitude. So in that sense, it's very pragmatic if I have a method that is kind of much slower than that, because I will basically not just see the direct effect, but I will have the multi-synapse connection or multi-area connection. So that gives problems in that area. And I'm not sure what the goal is there. And again, please forgive me, it's not like the field where I do most of my things. But if I could say, give you a list where this is the set of all pairs of brain regions, and we stimulated every one of them, and here's a beautiful measurement of what happens at the next one 10 milliseconds later. It's not clear to me to which level that would provide something that would feel like a satisfactory understanding of how the brain works and computes and things like that. But yes, that like is definitely something that like leads us into a space of thinking, like what is it that we want to provide? Now, let me maybe play the other side as well. If my attitude is primarily, I want to help patients, then in a way I don't care. Like there's only going to be so many places where I could zap them, and there's only going to be so many protocols that I could use for zapping them. And I could basically try and go through them, try them on the right patient groups. And in a way, like all the details of causality aren't actually so important once you're in that space, because like, yeah, if I find a place which works, which in a way we did for a lot of deep brain stimulation projects. And like, if you think about it, our theory of why it helps is often very, very limited. But like someone put an electrode there, it worked, and now we have standard treatments that follow down that path. So at some level, if we want this medical causality, it's almost like I'd argue what you actually want is the opposite, that in a way, let's just zap lots of places, see what's happening, might be very promising in that space.
Yeah, thank you very much.
Yeah.
I just had two more questions if we have time. I'll make it very brief if possible. But I also wanted to ask you about what you think about low dimensional population entrainment. You had mentioned that part of the problem with correlation was how high dimensional the space was. And if we say, well, we've recorded from all of these brain areas, you can still say, well, within the brain areas, the spaces are still high dimensional because the neurons can have different tuning curves and whatnot. But I was wondering what you think then about work that shows that when a population becomes active, almost the function lives in like this low dimensional space where you've got these certain kinds of population-wide entrainment mechanisms that go on. Like one of them proposed is divisive normalization. Another one which has been proposed would be modulation of individual neuron responses via local field potentials from populations.
So all those effects, they're all significant, not like p smaller than 0.05, and divisive normalization is clearly a factor for a good number of neurons, and there's clearly coupling of electric fields onto neurons there. Hey, that's why TDCS works. But at the same time,
we are talking about relatively small effects. So it's not that the vast majority of information is lost at that time because they tend to synchronize. Now, yes, they synchronize significantly, much higher probability than chance. But it's not that we lose all that much information. In fact, we might gain some information. It's a wonderful paper by Peter Koenig that shows that the relative timing of a neuron within some joint oscillation can actually carry very meaningful information, and does so in the visual system. So I think all these effects are real, but I don't think these effects actually lower the amount of information. And in a way, look, we can estimate how much information we take in. No, we can. There exist cases where people say talk about language, about like what matters. Yeah, a lot of things matter. And if you see a scene like right now, there's a lot of things in the scene that matter. It's not that really like I'm three-dimensional to you, or that would be very sad if I was. So at some level, I think that there's a certain amount of information throughput that just needs to be supported, and that clearly is. And if I look at machine learning, it's in fact really bad to choose a small number of features and stick to it. It's much better to have lots of them and just put small amounts of weight on like all of them. So the idea that the brain would go into a low-dimensional space, given that we now understand how statistically that's not such a great idea, I don't think that that's all that likely.
Okay, thank you. And I just have one more question for you. I'm sorry, these opportunities are so few and far between during the pandemic.
All right, we'll let you have one more. Okay.
All right, thank you. So I was also wondering about this potential turn away from causation. So you had mentioned that we might ask ourselves, why is obviously it's important to us, but is this the primary kind of route we should be taking the field of neuroscience in? And Dan Weiskopf has done some interesting work, kind of looking at the potential upshot of pursuing predictive versus explanatory investigations. And so I was wondering, you had mentioned neural networks explicitly during that part of the discussion. I was wondering if you didn't think it was important for interpretability purposes, as far as algorithms that are employed for certain kinds of, artificial intelligence applications, where we have, implicit targeting of minorities and things like that going on. Explanation of the way that the network is working and the way it's making these inferences seems to be particularly important for those kinds of things.
Okay, like that would be a whole different talk, but let me briefly dwell a little on like the neural network angle here. So if I build a neural network, I use maybe PyTorch, my favorite neural network language, and my code for building the neural network is compact. It's maybe 10 lines of code. Maybe, okay, there would be a very minimal, maybe 1,000 lines of code if it's a complex neural network. And I could take any one of you and spend 2 hours with you, and you would feel after talking with me for those 2 hours that you really understand this neural network. However, once it then trains, it sees millions of images, like goes to the world and does things, so plays millions of games of Go. So after that training, the weight matrix, and that is what we call causal interactions, the weight matrix, soaks up all this information about the world. And at that point of time, we shouldn't hope to be able to understand it, because the causal interactions after learning just contain all this rich information about the world. And whereas the code that makes the neural network, its anatomy, its learning rates, this is something that we might be able to understand much better. And now this gives up in a way on a certain promise that computational neuroscience has, which is understand how computation works to get somewhere. But I would argue that in a lot of domains, this will be fundamentally impossible. And in that sense, we need to say goodbye to a certain promise that the field had in the past that just I don't think we can deliver on.
Thank you so much.
Speaking of terminology, this is, I think, a twist that on the term functional connectivity from Ashkan Fageri. If I understand correctly, most of your issue with functional connectivity comes from the fact that you are relating the use of functional plus connection to causality. This might not be a good way to think about functional connectivity, though. In my opinion, functional refers to a linear mapping from a vector space into a field of scalars. Different FC methods are just a mapping from the vector space to a scalar field. What are your comments?
I like what you just said about the math is obviously entirely correct, but just read, just read the papers. And like, if you read papers on functional connectivity, essentially all of them, really, like I'm talking about 99%, will in the discussion section make causal claims. Let me give you a list of what the papers claim. They say, therefore, X is a candidate for medical treatment of something. Now, that means that you're willing to say that this thing causes the medical disease or anti-causes it, heals it. It's a causal statement. If you make a statement like, therefore, this is a mediator of something, mediation is a causal term. It means that A and B only communicate through C. If you say something of the nature, this shows a crucial role of X and Y. It's a causal statement because you say if X wasn't there, then there would be a problem with Y. Based on a causal analysis, which is supported by functional connectivity, you're not entitled to make those statements. So if you do, you're implicitly saying, I know I'm just doing functional connectivity, but I'll kind of think that it's causality. And if that's how you think about it, then you should say that out loud and basically make the statement that functional connectivity is a weak indicator for causality. And I argued in my talk why it's not a weak indicator for causality, why it's essentially unrelated to causality. And but basically, and that is a problem. Like, it is the advanced techniques that we have these days often use mathematical approaches that many of the users of these techniques don't really understand. In fact, I went to SFN a good number of years ago, and I had made a list of people who use dynamic causal modeling. And I just went from PI to PI, and I said, like, so you're using DCM. How does it actually work? What does it do? And the vast majority of them, in fact, maybe all of them, couldn't even describe what it does. For them, it's just a way of getting a graph, and a graph that they interpret causally. And I'm not faulting them for it. It's called dynamic causal modeling. It's just talks about causality within a model instead of causality within the brain. And it never anywhere claims that it's about causality in the brain. It's about causality in the model. And we compare a few models that are slightly different in the sense that the A matrix in that model is just different.
If I may ask a question, because you said something, I want to make sure I understood correctly. What I heard was you said correlation is unrelated to causation. You don't see.
Yes. So everyone, if I say that, is they say, no, yeah, correlation is not causation, but correlation is correlated to causation. But if you follow up the omitted variable bias equation, it suggests, like, yes, the correlation is positive, but the part of the positive correlation is factor 10 to the 11 smaller than the parts that are basically random, which means that it describes 10 to the minus 11 of the variance, which means for all practical purposes, it's entirely uncorrelated. Now, so this part of the logic, it's very important for me that everyone gets it. The logic is, yes, it's correlated. We have one beta, which is the real thing that shows us in the equation, but we have this other thing that's gonna have the same order of magnitude, only that is bigger by a factor of 10 to the 11, because we have 10 to the 11 terms in that part. And therefore, correlation in brain signals is actually not correlated with causation, or at least ex ante there's no reason. Now, like, there's all kinds of reasons why correlation might slightly correlate to it. What do you know? Maybe brain hemispheres don't talk all that much with one another, or maybe there's confounds with distance. There's like all kinds of reasons why in practice there might be some, but when it comes to the methods per se, there's reasons to believe that correlation is actually entirely uncorrelated with causation. And I think that that's important that everyone gets that.
Isn't that kind of a worst case scenario though that you're talking about? Because you're talking about making statements, causal statements about single neurons from macroscopic data, right? Are you not?
It's not about single neuron. It's about dimensions. If you say
Where did the 10 to 11th, where did that come from?
Yeah, so let's look at that. If you give me the average activity in a brain area, the question is, what does that mean? If the average basically randomly, if it's a random projection of the neurons that we have in that area, it would basically be equivalent statistically to a neuron. It would have contained the same information. Now let's be benevolent. Let's imagine you're lucky, which is the best thing that could possibly happen, and you hit the first principal component. The first principal component indeed is bigger than all other components in terms of the variance it explains. It just still only explains a small part of the overall variance, which now means, so here's the problem, that this principal component that I find in one area may very well be described by lots of neurons in every area across the entire brain. It's just that it's not amplified to the level of being the principal component. So I cannot know that. And so there's nothing about this projection that ex ante makes it better. It just makes it so that it falls on a dimension where you tend to have more power than a random projection.
Remember the early slide you showed the small system, right? And you showed how strongly related correlation was to causation in the small system, right?
Yes.
Now the large system, I guess one question I had about that, the 100 by 100 one, did you increase the number of data collected? I'm wondering if there's an estimation issue or if it would still be the same in terms of, because if you keep the number of samples the same, but you're estimating 10,000 more parameters, there's a bit of a computational issue, right?
So yes, you
estimation issue, I guess.
You do lose power. That being said, like
if you control the number of samples to match the number of variables that you're estimating, does it still look as bad?
It will still look roughly as bad. But that would see, like, this is wonderful, this discussion. Like the code is NeoMatch day 15. Anyone interested in it? Why don't you just go ahead, take the code, increase the amount of data to lead to fair comparison? We'll see about that. But in general, so here's, I think, the point that I want to imply on people. Now, so there is a scenario where the big system is a small system, which is every brain area only encodes one dimension. And therefore, the MRI signal that I get from that brain area is what every neuron does. In which case, I lose absolutely nothing. Now, we're still a big system, to be clear. Now, we still have 100 brain areas. But in that case, I wouldn't lose anything. But in practice, what really happens in reality, is that brain areas, like neurons in brain areas, they all mean different things, and they all project to many, many different brain areas. It's a relatively sparse. If you remember the Fellman-Van Essen graph, it's about 50% of possible connection actually exists in the broader visual system. So in that sense, but there's no, so the question is, can the small system, the neuron-neuron interaction system, be captured by the big system? And if it could be, if basically mean field was correct, then everything would be good. All problems would go away. It's just when I look at spike data, mean field doesn't seem like a very good approximation. So I don't think that, but that being said, look, let's sketch this space. you could say maybe we have strong interactions within each area and weaker interactions between them. You can take the day 15 of NeoMatch and just build in that clustering structure, and we'd see. You can say maybe.
My guess is it'll look better, but let's see. Someone should do it. Yeah.
Or like you could say, well, let's assume that it's not a random projection where it's like as if you have one mononeuron observed, but let's say it is the principle, it's the space of in every brain area you kind of get the first principal component. You can say, well, how much better does it get? This is all an open space, and I would love if there was spaces where we can say these are the kinds of things that we're actually entitled to say about it. It might be the kind of quality we usually look for, but it might be something that we can link to the theories that we have. But my problem in that space is that we basically moved towards industrial use of functional connectivity, where countless labs use it, but we don't actually know what it means. In fact, there's good reasons to be worried that even the fundamental assumption, functional connectivity, will at least somewhat be correlated to causation. There's good reasons to believe that's not the case.
I mean, what I hear, which I would completely agree with, is that we have to be careful about what questions we can ask given the types of data that we collect. And I believe that, we have the limited, the questions that we can ask are limited, right, in scope. Like you can't solve everything with one set of data that you've collected and make strong claims about it. So being very careful to qualify and think through what you've actually shown and being clear about stating the things that are often not said. Define your terms, qualify your results, etc. I mean, that's generalizing. It's not exactly.
Yeah, but it basically
those are the high-level principles I'm hearing. Yeah.
But if we do have correlational data, our discussion section should not make causal claims. Unless we're saying this is the exact theoretical reasons why I believe that in my specific case, correlation approximates causation. But then I want to see the exact modeling assumptions, and I would like to see if we can verify or disprove them based on data. Yeah. But it's basically, if people would say, so let me give you an example. If you say all neurons in one area do the same thing, and they're well described by the equation that Carl Freston uses to model excitatory and inhibitory neurons, then yes, I perfectly allow you to draw causal statements. It's just I will immediately call my spike guys and kind of say, okay, let's test if this model is actually correct, and let me just say it's not. And so basically, if we want to make these strong statements, we should be clear about what our assumptions are, which we don't.
I think that issue is kind of rampant in the field, and it's from a different perspective. I know Armin and I have been talking a lot about sort of, we tend to approach from like a data-driven perspective, right? Every model that people are using has its limitations, and so stating your model assumptions up front is really important as well.
But let me be clear. The modeling assumptions that allow you to draw causal inferences have never been stated, and yet everyone draws causal conclusions.
I have less of an issue with the with a sort of a weak statement about this result I've shown may point us towards a marker, right? Because I don't think that's saying it's not saying it will. It may be a waste of time. It may not lead you, if the correlation is not linked to the causation, but it's not technically an incorrect statement, I would think.
So yes, it is an incorrect statement in my view, and here's why. So so the statement means my method doesn't establish causality, but it makes causality meaningfully more probable. And what I'm arguing again is against that statement, because we all know that the press release is about exactly that sentence that you just said. But if our data didn't at all make the statement more likely to be true than before the paper, then we shouldn't say it. It's just not clean. It's just really confusing and it's really misleading.
So if you've used sort of a cross-validated predictive model showing that something is individually present in, I don't know, a patient group versus a control group, but it hasn't been designed as a study where you've actually, had an intervention, right? Then what can you say about that? What would you say, be able to say about that? Is it just correlation, even though it's been independently replicated in different data set?
So replication across data sets doesn't do anything. So keep in mind that the omitted variable bias does not depend on how many replications you have. You can replicate it on any number of studies. The confounding bias
depends on the question you're trying to answer.
Sorry?
Doesn't it depend on the question you're trying to answer?
Well, but the question that you want to answer to drive your treatment statement is, because the analysis that we did, it's more probable that this treatment will lead to positive outcomes than other treatments.
Well,
Which is a causal statement.
Yeah, you couldn't make a treatment statement about an associational study, but you could make a statement about, is it more probable that this is something that might be related to the disorder, right? Maybe this is something, that, we see a lack of relationship in this patient group compared to a control group, right? Is that not a useful piece of information?
Well, it is only a useful statement if it makes it more probable that the treatment would be helpful.
I mean, there's no treatment here, right? The statement is just that it might be telling us something about the disorder, right?
Okay, I don't
you don't know anything about treatment unless you, right? Because it may or may not be treatment relevant.
If the statement is, I hereby think that there's more activity in some brain area in a patient group, or that there's more correlation between two brain areas in a patient group, you're totally entitled to make that statement based on the data. Absolutely. I can say people with Huntington's disease have stronger coherence between these two brain areas. It's a totally fine statement. Mm-hmm. It's just then what do we do with that? No, you can say, I can immediately use it as a biomarker. Now, the problem with biomarkers is that we want the biomarkers to be good enough that they can actually drive clinical reality. But yeah, you can use it as a biomarker if it's strong, of course. And it's totally valid. There's no logical problem at all about biomarker research. If I can predict something that's clinically useful based on some data, it doesn't matter what it means. But at the same time, the fact that I can doesn't make it more probable that it's causal or something, which is in fact a statement that I occasionally hear. But people find that this is correlated with that disease, therefore that must be causal. No.
Right. Yeah. Okay, so I want to be sensitive to time. So we're about an hour and a half in. Armin, what do you think we should
So I can share the question on the Slack if it is okay.
I'm not yet on your Slack, I think.
Well, I think Armin can add you. So for the brain space talks, we typically have a follow-up Slack channel so people that didn't get to ask questions can interact. It doesn't have to happen immediately. It can sort of, we'll have it open.
Actually, I am on it.
Great. And then we'll also share the recording of the talk as well.
Cool.
And so we can kind of keep the conversation going and see if we can get people to be more careful with their language in their approaches. So. Great. Okay, so I want to thank you very much for your time and for this very stimulating conversation. And hopefully everyone has learned something from this. And someone go out and run that code and let's see how that works when you match the number of samples. I want to see the result.
Wonderful.
And follow us up on Slack, and we'll try to keep this going. So Thank you very much.